And the area that received the name Lake Lewis is upstream of Wallula Gap, which should be familiar to everyone. And it includes the Valley of the Yakima River, Valley of the Walla Walla, the Pasco Basin, and areas up the Snake River. So I tried to get the exact information on the naming, but unfortunately, the University of Arizona Library was closed down for the virus, so I couldn't get the original document. But the actual name, let's see, should be, okay, here we go. The second slide was conferred by First Lieutenant T.W. Simmons of the United States Army Corps of Engineers. And this is a diagram from his report based on the fall of 1881 expedition. You can see his boat here down the Columbia River. And the picture shows Victoria Rock, which you can't see anymore because Wanapum Dam Reservoir has basically inundated the area. And the scene is Sentinel Gap. So the expedition was going through Sentinel Gap and about to enter the Pasco Basin. So it would enter the area that got the name Lake Lewis. So the name officially appeared in the report, which was published in 1882. Probably named for Meriwether Lewis. So many things in the area were named for the Lewis and Clark expedition. There's not a lot in the report, but Simmons recognized the silt layers. He described boulders that may have been ice rafted erratics. And of course, he passed the White Bluffs, which are Ringgold Formation. He interpreted this as a ancient lake. And of course, the young silts that later got the name Touchy Beds and the Ringgold are of very different age. But his was a reconnaissance expedition. A more substantive report was then done by Israel C. Russell, who was a rather famous geologist. He worked for the United States Geological Survey and then finished his career as professor of geology at University of Michigan. And his report, A Geological Reconnaissance in Central Washington, was published as a United States Geological Survey bulletin. He reinforced the recognition that there had been a lake and recognized that this was a lake that occurred during the last glacial period. And in fact, he suggested possibly the lake was created by a glacial dam, which could have occurred in the Columbia Gorge because there were glaciers in the Cascade Mountains, and that area had not been fully explored for the glacial geology. So that was a possible suggestion. But he also suggested, and this was kind of an idea that was prevalent in the late 19th century, that an arm of the sea had entered the area because of the subsidence that would have been induced by the mass of glacial ice that was known to lie further to the north, because there was a large ice sheet that had covered what's now British Columbia. It was well known that it had extended into Puget Sound and was also in the northern part of eastern Washington. So if that had depressed the crust enough, then the incursion of marine water that would have been associated when the ice melted at the end of the last ice age could have entered the area. So also, just after this time period was the period when J. Harlan Bretz sort of emerged on the scene, basically in the earliest part of the 20th century. So this is a picture of the young J. Harlan Bretz, and many of you probably know that he had this unusual first name that used to kind of be a source of considerable controversy with editors of journals and books and the like, because his entire first name was J. And they were always wanting to put a period after it as though it was an abbreviation. But technically, of course, and Bretz loved to get one up on editors and the like, it's not possible to abbreviate a name that is just one letter. And so he got very righteous, all in fun, of course, with these editors. And some of you may also know that this first name, J, was a complete fake. He invented it. He wasn't born with that name. His birth name was Harley Bretz. And when he was a doctoral student at University of Chicago, he wrote J. Harlan Bretz on his dissertation, and his advisor, his PhD advisor, a man named Salisbury, looked at the dissertation and said, "What is this on your dissertation?" And supposedly Bretz then said to him, "Well, Harley Bretz didn't sound very academic, didn't sound like a real scientist, so I put this other name on my dissertation." Anyway, he became successful as an academic. He had been a school teacher and not into advanced work until the early 1900s, receiving his PhD in 1913. He initially held a job at University of Washington, but left after 1 year. He was not very happy with his colleagues because he didn't think they were very good scientists. I always like to tell my friends at University of Washington that story. He went to University of Chicago and was a professor there until his retirement in 1946. So there's a picture of him in his office. When he went to Chicago, he was in charge of the field course for advanced students, what today we would call graduate students. And here are some pictures of him with his students in the field. Initially, he'd take the train out to Portland, later to Spokane, and they would then go into areas initially in the Columbia Gorge. You can see on the bottom picture the typical field outfits, Smokey the Bear hats, and they had boots, and Bretz, of course, smoked a pipe.
I had a little trouble and you're kind of cutting in now.
Sorry? Did somebody have a question?
We missed that last bit.
I can't hear that. Is there something, is the sound all right for everybody?
It's okay. I can hear it, but can't understand it. It's garbled.
I hear you, but I didn't hear what she could say. What she said was garbled, but you're fine.
I'm fine? Okay.
Yes.
Maybe somebody's mic is not working correctly. Okay, so feel free if there's a problem to chime in. I'm happy to be interrupted, so don't worry about that. Okay, so this is these are his field parties, and the interest that they had at that time in the early 1900s, around 1915, 1916, when he would come out each summer, centered on these erratic boulders. This is one in Badger Coulee, which is not far from Kennewick. And the boulders were very striking because the landscape was either basalt or some other rock type. And then the boulders are granodiorite commonly, but there are other exotic rocks that could be recognized as coming from northern Washington or even from Montana or Idaho. And it was clear from geological background at the time that these had to be moved in floating ice. It was the only way they could get up to high elevations above the stream bottoms. Therefore, there had to be a large quantity of water on which these boulders could float in and be deposited on the landscape. So Bretz, in his first paper on the topic, published in 1919, and you notice the period got into this. I think I copied it out of a reference where they had put it in there. He inferred that the whole region from the Willamette Valley over in the west through the Columbia Gorge into the Umatilla Basin and into what later became called what was called Lake Lewis, but he extended the inundation up even into the Quincy Basin, was inundated by an arm of the sea. So it was a submergence that had been created by this effect of the ice sheets. Bretz told me if there was one paper that in his background of publications he would want forever erased and consigned to oblivion, it would be this one. It's an important thing because even great scientists make mistakes. And Bretz came to realize it was a mistake. Another interesting part of this is that he was studying the cataclysmic flooding in exactly the wrong direction. He was starting in the downstream part with the Columbia Gorge, and he was trying to think about the upstream part. But of course, the flood that he eventually recognized was coming from upstream and was going in the other direction. Now, he was correct that there was immense inundation throughout this region, and he was correct that there were ice-rafted boulders, but he had the wrong kind of water. It was fresh water and not salt water. But Bretz had an important thing that scientists have to have, and that is curiosity about what nature presents to you. And when he had been at University of Washington, before he started this field work in the Columbia Gorge, he had seen a topographic map of the area where my little arrow was pointing, right up here on the western edge of the Quincy Basin. And what he saw on this topographic map was an area called the Potholes. It's now the Potholes Coulee, which basically had the form of an ancient waterfall, but it was immense in scale. This thing is hundreds of feet above the Columbia River, which was on the map off to the left, off to the west. And above where the waterfall would be was the Quincy Basin. There was no river that was leading to it. The Quincy Basin, of course, he later recognized had filled with water, and that water had spilled and eroded back into the basalt, creating a giant cataract. But it was this anomaly that led Bretz eventually in the early 1920s to take his grad students up into the region that he named the Channeled Scabland. And that was upstream of the Lake Lewis area. So in the early 20s, Bretz described the features that came to be the classic features for recognizing the catastrophic flooding. He called the flood the Spokane flood because it looked to him as though the flooding had emanated from the margins of the ice sheet that came down to where Spokane is today. And these are some images from his early papers. He argued that the water had filled to hundreds of feet deep in various canyons, and it constructed bars that were also hundreds of feet thick. And these bars were like river bars, which are typically only a few feet thick, but they were on a greatly expanded scale. Also, the Aeolian silt, the older silts, which are partly indurated, called loess, had been eroded by this very deep water, creating scarps on the sides of hills like this one, and also small valleys perched up high near divides where the water had crossed from one valley to another. And these were called diversion channels. So you had a contrast, as shown on the right on the topographic map, between highly eroded basalt, scoured into potholes and channels and all kinds of chaotic looking terrain, from the smooth, loess topography. So in 1925, his paper, his first big flood paper came out in 1923. In 1925, he published a map showing the pattern. So up in the Northeast, there was, shown in the red, were the channelways that the region he called the channeled scabland. And this led downstream to an area where the silt deposition was located that had been noted by Simmons and Russell, shown in blue. And then through the Wallula Gap, there were more gravels and more scabland erosion down to Portland, Oregon, where there was a huge gravel accumulation. So Bretz recognized this as an immense flood, which he called the Spokane flood. And of course, this led to the big controversy. Here's a close-up. This is Bretz's map, and I've sort of penciled in colored to kind of make it a little more visible. So you'll notice the towns. This map was done in 1925. So the only towns were Wallula, Pasco, a town called Ringgold, and a town called Hanford. Of course, Hanford no longer exists. That's right about the spot where the reactor was that built the, made the plutonium for the Nagasaki bomb. That became, of course, the Hanford Reservation. And then Ringgold is, there may be a building there, but it's not really a town anymore. And of course, Wallula is there, and you have the Wallula Gateway. So the problem that Bretz had was there was a fundamental principle that had been established in geology. Freshmen taking geology courses learn about this. It's called uniformitarianism. And it was a principle that tried to put geology on a firm intellectual footing. See, the problem geologists have is they're trying to figure out what happened in the past. And we have no direct way to see what's going on in the past. That's kind of like not seeing what's going on in the future. But because of that, there were famous early geologists who tried to think, well, how do we put geology on a firm basis? James Hutton, Scottish gentleman, basically began this kind of thinking to say that we can be sure about what we can see happening now, and that we can be certain about. So we should begin with what we can see in action on the Earth today, and not invoke anything sort of outrageous beyond what's visible today. Charles Lyell, who was originally a lawyer before he became a geologist, argued very effectively that we had to employ what Isaac Newton called true causes, that geologists should not invoke, when they go back to the past, things that we don't see in action today. And of course, we don't see catastrophic flooding today, and therefore, geologists should be very wary about invoking cataclysmic processes. There is a fundamental logic problem with what these guys said. And it was pointed out that at the time they said it, and it is so fundamental that it sounds very almost obvious. And the problem is, who are we to say how nature works? Are we to say, the ones who say that nature should not have a catastrophic flood because we don't see one today? No, it's our job to figure it out. And that's exactly what Bretz did. But unfortunately, a lot of his critics thought that he was stating things in an irreverent way relative to how geology worked. Now, not everyone was that skeptical of Bretz, and one person who basically accepted a lot of Bretz's evidence, and he also was very interested in the evidence that relates to Lake Lewis, was Ira Allison, who was a professor at Oregon State University. And unlike a lot of Bretz's critics who sort of jumped on him in the later 1920s and 1930s, Allison went out in the field. He looked at a lot of the evidence that Bretz had presented. And he published a paper in 1933, a new version of the Spokane flood. Notice he says Spokane flood. He accepted that there was a flood. So in his conclusion, he says he agrees with Bretz there was a flood. And he agrees that there are the erratics, the scabland, the diversion channels, the perched gravel deposits. All of these things are records of this flood. But he developed a slightly different hypothesis, which was that there was so much ice that obviously had been there to create the ice-rafted erratics, that it actually jammed up in constrictions like Wallula Gap. And that this impounded water so that a smaller flow, although he didn't give the amount, but he thought it was magnified considerably from today because of the presence of glaciers, but that was able to build temporary impoundments. And those impoundments created areas like the Lake Lewis impoundment. You notice his conclusion is perhaps this revision will make this idea more acceptable, because he's still worried about how the geologists would think about this, as opposed to the way Bretz thought about it, which is, what is nature saying here? And if nature's not saying what my geologist colleagues are saying, who is the authority? Well, for Bretz, nature was always the authority. Here's a few more things from Allison's paper. He recognized the bedded silts, now called the Touchy beds, and he recognized that they had ice-rafted erratics in them. This is near Union Gap on the Yakima River. And you can see the bedding in the silts. And here's an ice rafted erratic. Here's a big one near Arlington in Oregon. Allison actually sort of plotted elevations of these things. They went up to about 1150 feet elevation back toward Wallula Gap. Near Portland, they were around 400 feet in elevation. This was not a pattern that would be made by marine inundation. It's more a pattern of ponding of water. But of course, Allison thought the ponding was created by ice jams, and actually the ponding was made by hydraulic damming, where the water, there's so much water it can't get through the constrictions. So in 1938, actually in the late 1930s, one of the main alternatives to the Brett's idea came into play. And the man who made the argument was Richard Foster Flint. And this picture of Flint actually reminds me of when I met the man. He was very tall, and he had this habit of looking down on people. I met him in an elevator, and I was a junior faculty member at one of my first meetings. And he's on the elevator, and he looked down on me, and I had the feeling like he was looking at an insect. He was a pretty austere guy. I met one of his famous graduate students and asked him what Flint was like as his professor. And this was George Denton, who's now a member of the National Academy. And he looked at me and said, I hated the guy. Flint was a very different personality than J. Harlan Bretz. And the two men probably had interacted with each other because Flint went to University of Chicago as an undergraduate. He most probably had Bretz as a professor. And I think that may have set up the antipathy that took place in that regard. Anyway, Flint published a very important paper because it was very influential in regard to the origin of the Cheney-Palouse scabland tract. Lake Lewis plays a big role in this because Flint tried to think of an idea to create the scabland area, and he did so based on an experience he had when he was a junior faculty member at Yale University, which he started in 1925. At Yale, there had been a very famous American professor, probably the most famous geologist in America and one of the most famous in the world, named James Dwight Dana. And Dana had in 1882 published on the Connecticut River and the gravel deposits that were there from the last ice age. These gravel deposits, and this is a profile along the Connecticut River from Massachusetts into Connecticut. And he recognized that the gravel deposits went up to a certain level, a couple of 100 feet above the modern river level. And he ascribed these to a catastrophic flood. Now, Flint, this junior professor without tenure, came in and looked at the broader glacial geology, pretty well known in New England, that Long Island and Cape Cod and Martha's Vineyard, these are the terminal areas of the big part of the Laurentide ice sheet that came over New England. So that's where the glacier terminated and deposited debris at its snout. But this ice sheet had stagnated, and when it did so, there were streams that flowed on the sides of the valley next to it. So that when the ice melted away, it left these high-level surfaces of the former streams that had been partially filling the valley. So Flint recognized that that you could get a whole lot of debris from an ice margin, and that this might be left on the sides of valleys, and there could be an irregular topography created that way. So in his paper, he suggested that the channels in the Scabland region had filled with glacial debris. So here's his profile going from near Spokane up here in the right of the diagram at elevations about 2,500 feet, where you had a large lobe of the Cordilleran ice sheet. And the gravel coming off of that filled the easternmost track of the channeled scabland called the Cheney Palouse, and it was graded to Lake Lewis, where the sediments are silts that were deposited, and he interpreted to a level of about 1150 feet. So the channels had filled, but Lake Lewis was not stable. It persisted for enough time for the scabland channels to fill, and then Lake Lewis drained away and the streams incised. And that incision then created remnants that Bretz, according to Flint, had interpreted as bars. So Flint had an argument that the scabland channels were not very coarse grained, that they were all fine grained material, and that instead of bars, you had terraces, and that the terraces were graded downstream to the silt in the Pasco Basin. And that silt, Pasco Basin silt, he named the Touchy beds for Touchy, and where the Touchy River joins the Walla Walla River. And at that point, just right near there, is what you might consider the type section of the Touchy beds. So there's a large surface called the Gadina Terrace, and this would be the type section. Bruce Bjornstad, who I think's in the audience here, described these sections for his master's thesis. Of course, the famous one that many of you have heard about is actually located within a couple, 2-3 miles, a little further downstream, called Burlingame Canyon. And we'll talk about that in a little bit. But the type section is here. And a couple of years ago, we were working in the field there, so you can see a bit of the scale. Here's 4 of the people looking at the site. One of them is my grad student, Dao Lu, and then there's a group from Britain that is there too. We'll say a little more about that later. This is from Flint's paper on the Cheney Palouse scabland, and this is his map of the impoundment that he interpreted as Lake Lewis. Now, Flint actually thought Lake Lewis was this whole area. Now a name has been given to the Umatilla portion, called that name is Lake Condon. But Flint thought that the reason that the lake had formed was because of landsliding in the area near present-day Bonneville Dam. And of course, there are landslides there. Basically, these develop because you have inner beds in the Columbia River basalts, or you have the basalts overlying soft volcanoclastic materials, and that creates a plane of weakness, and the material forms a mass movement that moves over that plane of weakness under the influence of gravity. This occurs on a massive scale, as near where the famous Bridge of the Gods legend developed, where about 500 years ago, the native peoples found that the Columbia River had been dammed, and it was possible to actually cross the Columbia River on foot. So these are some geological maps of the area. The problem is that the landsliding isn't that old, although there are landslides that go back into the Pleistocene. So also another problem was that the slide would only last a short period of time before the water would impound behind it and scour into the surface of the slide. So Flint's hypothesis is shown here in some diagrams that were in his paper. So he envisioned you've got an area with the Palouse topography on it. You have big stream valleys, and the valleys fill with the gravels that are coming off the ice margin. So the way this happens is up to the north, in the Spokane area, you have a lobe of glacial ice. The ice is flowing. Debris that falls onto the ice or is scoured from the bed over which the ice is flowing gets incorporated into the ice moving along the bed and carried to the front. As the margin of the ice melts, it erodes into this debris and carries loaded streams, braided streams, a way that can aggrade, particularly if a downstream area, the base level is rising, as would be created by Lake Lewis. So the stream terrace forms if you have a stream that has kind of developed in equilibrium with erosion equaling deposition, and something happens that disrupts that. And Flint argued it was the draining of Lake Lewis. The stream incisors, and then it leaves terraces. So here's how Flint envisioned that when the valleys filled up with water, they created diversion channels because the stream was flowing on top of a layer of gravel. So it actually created high-level scarps and flowed across diversions. And then in the incision, it removed the fill, leaving little remnants that, according to Flint, Bretz had misinterpreted as gravel bars. So that was basically his argument. Now, in the 1970s, late 1970s, when I was working to try to get Bretz the Penrose Medal of the Geological Society of America, I communicated with a lot of people that knew Bretz and knew things about the story. One of those people was Aaron Waters, a very famous volcanologist who had been born on the Waterville Plateau, located just up to the right of this aerial photograph, which shows the Potholes Cataract. Now, Aaron Waters did his PhD at Yale when Flint was a professor there. So he was a grad student. He wasn't Flint's grad student. He was a grad student of another professor. But he told me in a letter that he had told Flint back in the late 1920s, when Flint had read Bretz's papers and when Waters had read them. But Waters, unlike Flint at that time, knew the area. And he told Flint to go to the region right near the center of this picture. It's called Babcock Ridge. He told Flint to stand there and look across the Columbia River to the other side. And Flint never did it. If he had done it, this is what he would have seen. This is West Bar, and the Babcock Ridge is in the back of the picture, the Quincy Basin. The Potholes Cataract is just off to the right. The surface of West Bar is covered by giant gravel dunes. You can see the grain storage structures here. So these are immense. These are up 100 meters in spacing, up to 15 meters high. Flint never did it, never saw it. Anyway, Flint's ideas came into criticism from Allison, Allison did this paper in 1941 because he thought Flint was completely out of it in terms of his observations. Bretz, of course, knew that, but it wasn't just Bretz. Allison had been in the field and looked very carefully at things. Allison recognized that, let's see, get back to my original thing here. Okay. He thought that Flint didn't really understand the relationship of the gravel to the Touchy beds, because Allison saw there were many places where the Touchy beds were overlying the gravels, that in many areas the really coarse gravels were overlain by the Touchy beds. And he didn't think that Flint's idea about the Wallula Gap was quite right, because the features extended through the Columbia Gorge, where Flint had no argument for how these things came about. So Allison said that you couldn't explain these things piecemeal. You had to take into consideration the full relationships. So Allison, of course, thought that the full relationships required immense amounts of water. He thought it was ice jams, but of course, Bretz thought it was the Spokane flood. Well, I don't have time to tell the whole story about that, because I want to get into some of the more recent work. The outcome kind of got decided in the 1950s and 1960s. One of the most important things was a paper, and my reprint of it is shown here. It came from the authors. This is Bretz's signature. In the old days, before the internet and passing around literature that way, scientists sent out reprints, and they had covers on them. And this was a paper by J. Harlan Bretz, H.T.U. Smith, and George E. Neff. George Neff being with the Bureau of Reclamation in Ephrata, Washington. And this paper was published in 1956. It relied upon important work by Joseph Thomas Pardee that in 1942 showed that the ice dammed lake, Glacial Lake Missoula, was the obvious source for the water. Pardee described these large-scale gravel dunes, and in the 1956 paper, Brett Smith and Neff described many of them throughout the Channeled Scabland region. By the 1970s, we had satellite images that showed the Cheney-Palouse Scabland tract and other areas of eastern Washington. So on the right is a Landsat image. It goes from the Spokane area in the upper right down to the Snake River, the Palouse Falls area in the lower left. The pattern of the eroded basalt shows up dark. The wheat fields on the Luss shows up in the light pattern. You can see a checkerboard pattern at higher resolution. And if you look in any detail of this area, you see exactly the kinds of features that Brett's talked about. The gravels are not terraces, they are bars. In many cases, they're pendant bars that developed downstream from bedrock obstructions, downstream from isolated Luss hills. This is a map that was made by one of my students in the around 1980, when we were doing a lot of our work in this area. My own connections with Bretz began with my PhD dissertation in the late 1960s. At that time, I communicated with him. He reviewed my whole dissertation, which was finished in 1971, published in 1973. I didn't interact with him personally a lot until the later 1970s, when I was doing the NASA guidebook to the Channel Scabland. But I also was preparing the nomination of Bretz for the Penrose Medal. And so I interviewed him quite a lot about the Scabland stories. Yeah, that's Bretz on the left and me on the right when I had hair. At least one of us did at that time. What I did in the early 70s, well, starting in the late 60s for my dissertation, was something that Bretz had conveniently left undone, which was all of the physical quantitative arguments for how the catastrophic flooding worked. When Bretz proposed the flooding, there were many geologists who said it was physically impossible that so much water moving so fast to do what Bretz claimed just would violate rules of physics. Turns out that was totally wrong. Totally, because in order to create the features that you have in the channeled scabland, you needed to have exactly that kind of flow of water. The physics was all completely consistent with Bretz's idea. By the way, this is one of those little tiny leisurely stream particles that Flint thought occurred in the channeled scabland. He obviously did not really do much field work. This particle is about 20 meters long, and it was moved by Missoula floodwater, was actually moved near this area called Soap Lake. If you look at the physical parameters, you find that the water flowing in the scablands was incredibly fast. 30 meters per second is about the speed that you drive on an interstate highway. And if you can imagine water moving at that speed, the energy is incredible, because the energy goes up with the velocity squared. So the ability of water to move particles this big is a reflection of the rate of energy expenditure. And that explains much of what we see in the channeled scabland. Now, Bretz, obviously Bretz, Flint, they tried to make some estimates as to the amount of water. Flint, in his 1938 paper, recognized that Wallula Gap had a scabland at the top of it. Bretz had described that. Now, for him to explain this scabland, which was up, here they say 1,100 feet, it's more like 1,200 feet. For Flint, the whole Pasco Basin would have to be filled with gravel in order to get the streams up to that level. And Flint actually made some calculations about how the water flow would have occurred from the Columbia River. And the discharge of the Columbia River, he estimated at about 5,600 cubic meters per second. Now, Bretz, back in the 1920s, recognized that his Spokane flood had to go through this, but Bretz didn't know how to calculate a discharge. He told me, and this is a typical Bretz story, that that early in his career, he didn't want to be a geologist. He wanted to be an astronomer. And when he got to college at Albion College in Michigan, he took his first astronomy class and discovered that a lot of it was about mathematics. And he said that at that point, he realized that when he was young, he fell out of bed and hit the side of his head, which was the part of the brain that did mathematics. And he claimed that that's the reason why he decided to go into geology instead of astronomy. But in the paper in 1925, he had an engineer calculate for him the flow through Wallula Gap and it came to 20 million cubic meters per second, actually 66 million cubic feet per second. We now use metric instead of English units, but Bretz gave it at 66 million in his paper. It turns out that calculation was a bit too conservative. In my dissertation, I got 9 million with more sophisticated model. My PhD student, Jim O'Connor, and I did a paper, and we got 10 million. And that has been confirmed by later work. This is work by my former PhD student, now postdoc at University of Arizona, Dao Liu, who has been using two-dimensional hydraulic models. Basically, these show the dynamics of the flooding through the entire region. And now you can see with a quantitative computer model how the water coming in from northern Idaho, from the position of the ice lobe for Glacial Lake Missoula, entered the Channeled Scabland region, and that same pattern that Bretz recognized in, actually even in his 1919 paper when he thought it was marine inundation, we can see it recreated by the computer. The deeper water is blue, the shallow water is lighter color. Here is what came to be called Lake Lewis, the Yakima Valley, the Walla Walla, the Pasco Basin, Lower Snake River, flowing through the narrow constriction of Wallula Gap into the Umatilla Basin, through the Columbia Gorge, into the Willamette Valley, and then out toward the Pacific. It's possible to show the timing of how the flood, actually there were multiple floods, we'll get to that in a moment, but how a very large flood went through the region. The timing in hours came to about, by 100 hours or so, it was in the distal parts of the Willamette Valley and had gotten out to the Pacific Ocean. It was getting into the Pasco Basin area about midway through the flood passage, about 50 hours. It took about a couple of days to get into that area. The energy expenditure, the velocity, the high velocity areas are shown in red and yellow. The ponded water areas are shown in blue. The Willamette, much of the Yakima, Walla Walla, lots of the Pasco Basin was ponded water. Quincy Basin was ponded water, but there were areas of high velocity that are shown in red. We can show all of this now with advanced computer models. Another thing that we've been doing in the field, this involves those ice rafted erratics, is we can use a new technique of dating, basically, that relies upon the isotopes that are created by cosmic rays in the surfaces of rocks. Here I am, I think this was when I was in the field with Bruce Bjornstad up on the Scabland atop Wallula Gap. We sampled a boulder there that came back with a age of 18,000 years, which had to have been a very large flood that was able to inundate up to that level. So the general ages we're getting from this technique are, many of them are around 16,000, but they go back to about 18 or 19,000. The 16,000 date is associated with a volcanic tephra, the Mount St. Helens S tephra, located at many areas through the channeled scabland. It's often found in the Touchy beds. It's occasionally found in some other stratigraphic units. Now, the Touchy beds received a lot of attention beginning around 1980, when Richard Waite from the United States Geological Survey looked at the sections that Bruce Bjornstad had looked at for his master's and others had looked at. He produced a very detailed stratigraphic analysis of the Burlingame section, where 40 or 41 units are found in where there's coarse grain beds shown in yellow, fine grain. The coarse ones can be sand and even a little fine gravel, and the fine ones are silts. And these have distinctive sedimentary structures, really magnificent detailed section in this exposure that was created at Burlingame Canyon. Now, Richard expanded this idea to infer that he could correlate throughout the whole basically northwestern pathway of the floods, all the way from the deposits in Glacial Lake Missoula that include varved lake sediments and what he interpreted as drainage coarse material when the lakes drained, through the glacial lakes Columbia and Priest Lake in northern Washington, to the Touchy beds of southern Washington that we talked about, and then to the Willamette silts. And so he inferred in good traditional stratigraphic fashion that you could go bed for bed from all the way from Montana to basically into the Willamette Valley in Oregon. So here's where some of these sections are located. Glacial Lake Missoula, these green ones are sections measured there. Here's Priest Lake up here. Glacial Lake Columbia sections in here, and then various sites with Touchy beds or units that are equivalent to Touchy beds in where Lake Lewis is located. So a couple of years ago, we were in the field looking at the type section, and here's a group from Aberystwyth University in Wales that were with us. Alan Roberts, who does optical stimulated luminescence dating, and a visiting postdoctoral student, Svenja Riedesel, and then Nick Pierce, a tephrochronologist. And you can see they're looking at the Cetes tephra. And here's a more distant view of that. And you can see that there are a number of beds. If we went back to the Richard Waite diagram, I think, see if I can go back. Okay, you can see that the Cetes tephra is located at bed 29, and up at the top, you're at bed 40. So there's about, no, let's see, I guess that's bed 28. So bed 28, bed 40, about 12 or 13 beds above the Cetes tephra. If you look at the diagram here, you can see all of these beds. There's about 30, not 30, there's about 20 that are above the Cetes tephra. So basically what you see here is that 3 miles away is a different number of beds above the Cetes tephra as in Burlingame Canyon, which poses kind of an interesting question. How do you correlate all the way from Glacial Lake Missoula to the Willamette Valley if they don't even match up a few miles away? The Cetes tephra matches up, but clearly there's some issues in regard to the stratigraphy. Well, this is sort of an ongoing problem. There are other sites that are being looked at, and this is one that Bruce and I and others have been looking at, the famous White Bluffs that Simon saw when he was coming into the Pasco Basin, mostly exposures of ringgold, but there is a channel that was cut into the ringgold that contains basically bedded deposits. That they're not, they could be called Touchy beds, but they're coarser grained. And our preliminary work shows they contain the Cetes tephra. but they have much more complicated kinds of stratigraphy. We're currently trying to do better work on these to get the dating on them. We have other lines of evidence that have now come about. The groundwater in the Pasco Basin contains evidence of recharge of glacial water, which is shown by the isotopic composition, basically the oxygen isotopes, and the radiocarbon dating can show the age of the groundwater. And what we find is that the period of time of the Missoula floods, around 18, 19, 16,000 years ago, we definitely have that influx of water. But we have evidence of major pulses of groundwater that's isotopically similar going back 30,000 and maybe even earlier, contrasting quite a lot with the modern groundwater. And there's also a marine record out in the Pacific Ocean where the flood water basically entered the Pacific Ocean and left deposits and also effects on the salinity of the ocean that are represented in the deep sea sediments. And these go back to older, to 30,000 and more in terms of the peaks of fresh water influx, probably from catastrophic floods into the oceans. So here's a North American map showing the big ice sheets toward the end of the last ice age. The area we've been talking about in the Scablands is just this little corner here in the northwestern US. But the area affected by the flooding out into the Pacific goes 2,000 kilometers. Moreover, in the decades since about the mid-1980s, numerous other manifestations of massive flooding has been found in North America. Indeed, all over the world, associated with the areas where large ice sheets were located at the end of the last ice age, about 18,000 years ago, we have evidence of what are now called megafloods. These are flows of water, fresh water, associated with glacial margins in the excess of 1 million cubic meters per second, the kinds of flows that occur but much more slowly in ocean currents. This is a review I did with Paul Carling, who also does this kind of work. We find these things all over the world where there are big ice sheets. In North America, the ice sheets covered a large area. You had big lakes and outflows. They were even bigger in Europe and Asia. All of this has been discovered recently. Jay Harlan-Bretz had no idea that what he was studying was actually something of global significance. He thought that maybe the Scablands were unique. They were not. This sort of thing was happening all over the planet at the end of the Ice Age. But it gets even more bizarre. By the way, here's one of the big boulders. This one is in Siberia. This was moved by the floods there. There's a giant bar in the background. Here is a giant bar, a couple of 100 meters high, also in the southern part of Siberia. This is on a river called the Katun. But as I said, it gets more bizarre because even bigger floods occurred on the planet Mars. In the ancient past, more than 3.5 billion years ago, there were immense flood channels that occurred on Mars, so much water that they created a large water body. Lake Lewis is tiny compared to what the massive floods did on Mars. They inundated the entire northern plains of Mars. So here is a rendition from NASA topographic data showing one of these immense flood channels on Mars. It's up to 400 kilometers across. And the northern plains of Mars, the area shown in blue, was filled with ponded water that emanated from actually outbursting from subsurface reservoirs onto the surface of the planet. So if J. Harlan Bretz were alive today, he'd be absolutely amazed at what his outrageous catastrophic flood idea had done. And if I haven't left some questions for you to ask, then probably you weren't paying attention, because there's a lot of stuff in what I covered. I'd be happy to take any questions.
I have one. Am I on mute?
I hear you.
Oh, I was impressed by that graphic you showed of the Northern Hemisphere and how widespread there were of floods throughout Europe and all around the Northern Hemisphere.
Yeah, that's a big story. Yeah.
And you didn't show anything in the Southern Hemisphere.
But, yes, I showed, I would have had to point it out. The one thing about the Southern Hemisphere, there's not a lot of land in the Southern Hemisphere. And much of that land is equatorial. So you have, the Brazilian rainforest, and you have equatorial Africa. And as you go further south to where you get glaciation, South America goes to a big triangle. Well, in the southern part of South America, there was a big ice sheet called the Patagonian ice sheet.
That's the one I was thinking about.
And the Patagonian ice sheet had catastrophic floods. And those catastrophic floods have been studied recently by a former postdoc of mine, Gerardo Benito, who is at with CS is with the Spanish government scientific agency. I particularly like those floods because they occurred on a river that flows from Argentina to Brazil called the Baker River. I'm not kidding. It's called the Baker River. And it had the biggest floods in South America. If you study floods your whole career and having, some of the biggest ones being your name, kind of, I don't know.
The Patagonian one is a particular interest because I saw a video a few years back that described that one as being an ice sheet that flows over a valley, and almost annually, like clockwork, it breaks up.
Yeah, that's the present day ice sheet. And that there's a big issue with that because the Brazilian, the Chileans are trying to put in big hydro plants on that river. And if it floods with glacial floods, that's not very good for your dam. In fact, that's one thing we do when we put dams on rivers. The people who try to sell you on the idea of having a dam on your river, they never tell you that if the dam fails, then you'll have a bigger flood than nature would ever do. And all dams have a finite risk of failure.
Yes.
You cannot build a dam unless there is a risk of failure. So that when they build dams, they never tell you that there is a risk of the dam failing, and when it fails, it will be stupendous and cause tremendous damage. They try to say that the risk of the dam failing is not very great, but they don't really know what the risk is. I'm an expert on this, and I can tell you, they don't really know. The only way they can know is studying what has happened in the past, and engineers don't do that because—
And they only have one of a kind to start with.
Yeah, so this is another whole topic of mine. I work on big floods, even the big floods that occur when people are around. Mm-hmm. So any other questions?
Oh, what was the origin of the tephra? Was it Mount Rainier? Do we know?
Well, the one we've used as that marker is a St. Helens tephra. St. Helens was very prolific there was a sequence of tephra called the S sequence, and it had multiple events in it. It occurred over a few thousand years, not unlike the 1980 thing that happened, but it was unique in its association with the Scabland deposits. Another important source was Glacier Peak in the northern Cascades. It produced a tephra around 13,000 years ago, and it is found in some of the Scabland deposits. There are some other tephras that are found in the region as well, but St. Helens and Glacier Peak are the main ones that we can find them. And of course, these tephra have to be identified by their mineral composition. They can be dated at the volcano source. Typically, it's difficult to date the individual little tiny shards of glass, but you can date larger mineral grains in the eruptive area. And the tephra can be associated with materials that can be radiocarbon dated. And that was basically how the St. Helens S tephra was dated at 16,000, was associated with carbon datable material.
I have a question for you. There's some relationship appears to be between the size of the floods, or at least the elevation of Lake Louise over time. Can you expound on, any general concepts as far as are the, the older floods, were they, did they create a higher stand of Lake Louise compared to younger ones? I mean, that's kind of the way we think about it, but I'd like to hear your thoughts on that.
Yeah, that's a good, what we call a working hypothesis, and it seems consistent with evidence that we're seeing in other areas. In Lake Louise, you're mainly dealing with evidence of water stands, and obviously the highest evidence that is going to be associated with high-level silts and ice rafted erratics is going to give you a particular point. I mentioned the erratics on Wallula Gap, where we got an 18,000 date. And we have, well, of course, these dates we have to be very careful with, because there are ways that they can be thrown off. That big boulder that I showed early on that is in Badger Coulee, we actually got a date of about 33,000 on that one. But we have to be very careful. That could be an inherited age. But the very important for this is putting together what Allison talked about, is the pattern throughout the region. And in the Columbia Gorge, Jim O'Connor and Gerardo Benito, I mentioned Gerardo before, they basically found pretty good evidence for the sizes of floods because of dating deposits that got up to a certain level and things that went through gaps and deposited on the other sides of those gaps. And what they basically found was that a lot of floods were generally, they were mega floods. They were 1 million, but they were like 1 million, 2 million cubic meters per second. And the number of floods that were up really big, up 5 million, 6 million, they decline. And then maybe what in the gorge got to about 10 million, maybe just 1 or 2. And it appeared that those might be older. And that, so that the pattern involved early phase of massive flooding and then a later phase of smaller floods. if you go to the basin of glacial Lake Missoula, way up where, you know, Richard wants to correlate tushy beds to the fine beds. Those lake beds that he correlates to in glacial Lake Missoula are inset against massive, huge gravel bars. In other words, those outflows from glacial Lake Missoula that correlate, or he correlated to the tushy beds, were not the big outflow. And interestingly, J.T. Pardee pointed that out in his 1942 paper. He mapped the relationships, and those fine beds are inset against the big catastrophic outflow features in glacial Lake Missoula. And those are older. We haven't dated those directly. We know the relative ages. And so a working idea is that that big outflow is somehow associated with the earliest big flooding in the, let's say, the Pasco Basin and through the Columbia Gorge. And that the rhythmically bedded glacial Lake Missoula sediments, they're outflows, but they may be outflows that were generated not by a massive break of the ice sheet, but by the usual kind of yokel out flooding. And it's actually the kind that Waite described in his paper, where the water basically lifts the ice dam, flows out underneath, the lake drops, the water pressure goes down, and the ice then slams back down again. And so you have a flood, a big flood that's released, but it actually is not the kind of flood where the whole ice dam breaks and you have an 800-meter high wall of water that comes down. That seems to have only happened early, and it didn't happen in the later flooding. So I'm giving you a kind of long answer, but it's basically looking at the whole picture of how the flooding was occurring throughout the region. It's kind of like the, you know, the blind man and the elephant. You're looking at, you know, parts of it and you're thinking some of it's working this way and some of it's working that way, but you have to see the whole thing. And that's why it's such a difficult problem to get one's hand around. But it's very typical of geology that in order to understand the vagaries of the past, you have to put together all the evidence that you can marshal, and you don't always find it where you expect it.
Well, thank
Other questions?
I really enjoyed your talk. It was awesome. Thank you very much.
Oh, okay. Well, glad you were on that trip.
No, I saw, Chris, you had a question posted, right?
Yes, please. Yes, please.
Yep.
Did it come up? How do I do that? Or do I just say it?
Just talk.
I'll just talk. I noticed on some of the previous slides, it shows the path of the great floods and the inundation of water. And yet it seemed to me that the picture of the gravel bars, the really distinctive gravel bars that are near Quincy, that you indicated, it should have been an obvious indication of catastrophic flooding. They don't appear to be in the path of the big flood. They appear to be slightly north and west of the big flood, or am I looking at that wrong?
They were, if you're talking about West Bar, that was flooding
Yes.
that came down the Columbia River. And there is a complex story there that involves the Okanagan lobe of the Cordilleran ice sheet. That Okanagan lobe advanced across the Waterville Plateau, cut off the access of the flooding through the Columbia that went down the Columbia before the Scabland flooding, but that lobe itself broke up and created flooding that went down after the major flooding. And that
The time period?
So we're still working on the dating of that, but we know we had scabland flooding that was occurring 19,000 and probably earlier than that. That we had scabland flooding that was associated with the Tushi beds at about 16,000, and the Okanagan lobe seems to have been advanced across the scablands, forcing water through the Grand Coulee, the Telford Crab Creek area, the Cheney Palouse, maybe around 16,000, but that broke up after that, 15,000, 14,000, and flooding then was able to go down the Columbia again. And that's when West Bar was created. Okay. West Bar was created by later massive flooding that was able to go down the Columbia River after the ice came back. Basically, we're getting a much more complicated picture. Another part of the story is that we may have had flood water that was being introduced by sources other than Glacial Lake Missoula. We know that as the Cordilleran ice sheet receded back into Canada, we got late flooding after Lake Missoula was gone from ice dammed lakes in Canada. But we may have also had flooding associated with the fully advanced Okanagan lobe and the fully advanced ice sheet that came out from under the ice, because we know in many parts of the world we get that kind of flooding coming out from under ice sheets. So that was possible.
Is that superheating from something like a volcanic activity under the ice sheet?
That was, there's an interesting story on that. Bretz himself, when he was having trouble explaining the catastrophic flooding in the 1920s, went into southern Canada and searched for subglacial volcanoes. He was onto something there, but he didn't find them. It turns out they are there. They were further north than where he looked. There's an area called Wells Gray, and in Wells Gray there are what are called in Iceland Table Mountains. These are areas where volcanoes erupt under ice sheets, and they are there. So there was a mechanism to generate subglacial volcanism type flooding. There also seems to have been a big subglacial lake where the Lake Okanagan is in southern British Columbia, there was a massive subglacial lake there that could have basically, because of pressure effects, erupted onto the surface. All of that is under current investigation and out there with the sort of working hypothesis ideas. So the Scabland saga goes on. There's plenty of work for people to do, and I'm not going to finish it. It was just my pleasure to be a part of the parts I dealt with.
Well, thank you. It was a great lecture. It's terrific. Thanks.
How many floods were there?
Well, if you talk to Richard Waite, he's got up to about 90. The more interesting question to me is how big were all these different floods? Clearly, there were multiple flood events, but they were of varying sizes. And I think the really big ones were the ones that did a lot of the important work in creating the Scabland topography. But that also is a story we're working on. There are, if you go with the one bed per flood and you look at the low energy deposits, which are the Tushi beds or the lake beds in Glacial Lake Columbia, you can get up to 90 or more separate events.
Thank you. And were there any civilizations, human civilizations at the time?
It used to be thought that the humans that came into North America did so in the time period prior to the major mega flooding, the so-called Clovis culture, which was associated with a particular type of projectile point. That idea, there certainly were people there at that time. So 13,000 years ago, there were people. 16,000, only relatively recently have we now found for sure there were people older than 16,000. And the current thinking is that those people did not come in the same way as the Clovis people. They actually came along the coast, but at that time, sea level was very low because you had the ice sheets that had taken up the water from the ocean. So those people were migrating along an area of coast that is now under the sea, and therefore their evidence is not readily discernible. But if they were migrating along the coast and relying on coastal resources, marine mammals, there would be a lot to eat. There's a reason why that would be a pathway. They would have experienced the cataclysmic flooding because it came through the Columbia. And that would have been pretty impressive, those that survived. But it isn't just North America. Those maps of the whole northern hemisphere, there was catastrophic flooding going on near the end of the last ice age, all around the big ice sheets. And there were people around those ice sheets. And it's not too far-fetched to recognize that almost all those human societies have stories of massive floods that for them inundated the entire world. Those stories are probably real experiences that were told generation to generation because such massive floods did occur when there were people around.
Thank you.
Well, I thank you for letting me talk about my favorite subject. I've been studying catastrophic floods. I've been a professor. Next year is my 50th year, 10 at University of Texas at Austin, and it'll be 40 at University of Arizona. I got interested in the catastrophic flooding of the Northwest when I was living in Fort Lewis and then Bothell, Washington. I made a flour and salt topographic map of Washington State in 8th grade. And the two things that impressed me when I was doing the topography was the Channel Scabland and Mount Rainier and the volcanoes. So I decided later, I got hooked into the Channel Scabland for my PhD in the late 1960s. And I've been studying catastrophic floods ever since. It was helpful to know J. Harlan Bretz. He was, I could go on about him as a person, total different kind of person than Richard Foster Flint. Rather amazing. His students loved him. I mean, he was a tough guy, but he was famous as an educator. So when I did his Penrose Medal, it was amazing the people that came forward to write. I mean, these were the top geologists in the country. They were geochemists and geophysicists. I mean, on one of the field trips I led, I don't think it was the one George was on, M. King Hubbard, one of the most famous geophysicists, was on that field trip. And he was there. He told me to make sure I did justice to J. Harlan Bretz because he wasn't going to let me say anything bad about him because he had Bretz in school and was going to make sure that I did right by him.
the amazing thing is that Brett's drew all his conclusions without the satellite imagery and without all the aerial photography. That's it. You're talking about you're looking at an elephant piece by piece. That's, yeah, amazing to be able to put that story together.
Well, he was a classic geologist in that he let the scenery, the sediments, the features tell him the story. And when people who thought of themselves as his betters said that wasn't, that didn't fit the theory, Brett's view, if the theory doesn't match what I see in the field, I'm going to throw out the theory. And that Brett's was stubborn. I mean, famously, when he got his Penrose Medal, he was, the GSA gave him that in 1980. And he was then in his late 90s. He couldn't attend, but he wrote for his daughter to read it. And in the end of the acceptance, he said he had a big regret of this whole Scabland controversy. And his regret was that he had outlived all his critics and he couldn't gloat over them as he received this medal.
Can't blame him for that.
Yeah, if you read the story, John Sonicson wrote a biography of Brett's called Brett's Flood. And I interacted with him quite a lot on what he was doing. By the way, he didn't get it all right in there, but that's the way these things go. But it's good that he was able to interview a lot of the Brett's family and do all the work that was necessary to get the biography. It's an interesting read to find out something about him. Brett's himself published a bunch of memoirs in kind of a disjointed fashion. And Sonicson used a lot of that material. Brett's loved to tell stories. So he had lots of great stories about all of his experiences working through the Scablands and the like. He had a lot of stories about Flint too. The two were, let's see, diametrically opposed personalities.
I have a question about Flint. I work for Washington State Parks, and at Palouse Falls, one of the signs and a lot of the lore around Palouse Falls and Richard Foster Flint is that he was standing at Palouse Falls and looking at the falls and apparently famously said, "How could anyone have been so wrong?" referring to himself. Have you heard that sort of legendary thing before?
I know the story, but it wasn't Flint. He never admitted he was wrong. That would be totally contrary to Flint. In fact, Flint published in the early 70s a massive book on the Quaternary period, glacial and Quaternary geology. It was the most Flint was like an encyclopedia. He was meticulous in detail. He covered literature in great detail. His failing was being able to understand what was going on in the field. And that's what Brett's did mainly. Brett's didn't ever write major books. Brett's wrote a textbook one time, which was pretty bad. Brett's was let nature tell me what's going on. Flint was the guy who looked on all the details. Anyway, in this book, Flint, probably the most fascinating thing in the entire Pleistocene is the Missoula floods, and we now know they're even more important. He had one sentence on the Missoula floods in which he said, and he gave a quote to Brett, not a quote, a reference to Brett's, that there was in the northwestern US some massive flooding of unusual character, something like that. I don't remember the exact quote. That's all he said. No, if they had it at Palouse Falls, the guy who said what you said was James Gillooly. James Gillooly was a very famous structural geologist. I saw him when I was a grad student in Colorado in the 1960s. He came and gave a lecture there. But Gillooly was when Bretz was trying to defend his hypothesis in the late 1920s, Gillooly was kind of a young Turk, and he thought he was really very clever, like many young people do. And he had a very elegant criticism of Bretz's hypothesis, where he did some quantitative stuff and tried to show it was wrong. And so Gillooly got well known for being a critic of Bretz. But when Gillooly went out in the field and was shown around by some of the other geologists, this was after Bretz was not so active anymore, that's when he went and he wound up at Palouse Falls, and he just started laughing, about himself, that he'd been so wrong. Yeah, that story, I forget who told it. It was in the material that I collected for Bretz's Penrose medal. Gillooly, I'm not sure if he was still alive at that point, but anyway, it was Gillooly who said that.
I saw a question coming through the chat. Is the mechanism of multiple ice dam releases being better understood? Is it ice lifting or hydrofracturing?
The problem with the ice dam failures is that the ice dams are gone. The flooding destroys all the evidence. So what we say about those ice dam failures is indirect. We have to reconstruct them. It's kind of like a crime scene where somebody shoots a weapon. You don't have that weapon shooting. You have indirect evidence of that weapon. Maybe you don't have the bullet, but you have the energy indicated by the projectile from the bullet as it entered into a piece of wood that tells you the velocity of the projectile, and certain kinds of guns would have a certain kind of velocity. So you can try to work back to how the gun was that fired. It's that kind of thinking we have to do for the ice dam failures. And it's not going to tell us exactly what happened, but to release a flood of a certain size and a certain amount of energy, the ice dam would have to fail rapidly, allowing a certain depth of water to rapidly come out. So one can try to work back to some of the kinds of failures. One can also look at ice dam failures that occurred today. And we've mentioned some of these, that you get flooding that lifts the glacier and the water comes out underneath it, and then the glacier slams down on top of it. You get flooding where the water flows long enough that it creates a tunnel into the ice. It actually it melts the ice, creates a larger and larger tunnel, but as the level of the lake goes down, then the pressure to feed that water decreases, and eventually the tunnel closes up because the glacial ice flows into the area. But you can also get the water moving around the edge of the glacier and eroding into the ice mass. If it comes under it, it can break up the whole glacier. Part of this depends on how active the glacier is. If the glacier is still moving and feeding more ice in, then it may be in a different kind of state than a glacier that is stagnant and is decaying. Probably when the glacial Lake Columbia was released from the Okanagan lobe had advanced and then was in a state of decay, and the flood was released because the ice was weakened in that kind of way. I'm just giving some of the kinds of thinking that a geologist would have to do to figure this problem out when the actual ice dam is gone.
Thank you very much for your time. Very interesting. Appreciate it.
Okay, well, thank you for the opportunity to talk about my favorite subject, really big floods.
Everybody unmute and clap.
Okay.
Thank you so much.
You guys are doing the right thing. A group that is into big floods.
Yeah, it was really great. Really enjoyed it. Thank you.
Okay.